Welcome everyone. My name is Johan Stokking. I am tech lead and co-founder of the Things Network. Who of you knows the Things Network? Oh, that's very nice. I'm going to talk about scale, but first of all, I think it's good to talk about a little bit about Internet of Things in general. Because Internet of Things in general, we know the Internet as the Internet of humans. It's designed for screens and for human interaction. So existing wireless technologies are designed to have very low latencies, to be always connected, and also Wi-Fi, for example, to stream 4K Netflix. But Internet of Things is different. Things, they don't have a day rhythm. They often don't need very low latencies. And for the Internet of Things, current Internet of Things solutions, they often use wireless connectivity that's actually designed for human interfacing. For example, Wi-Fi, so Raspberry Pi has a Wi-Fi connection, cellular, so you see many sensors that are deployed in the field that have a SIM card, and also Bluetooth that's actually more designed for personal area networks. And if you look at the growth of the Internet of Things, and this is basically, I don't want to mention Gartner all the time, but it's always good to have a look at the predictions, and not only the numbers, but also the growth of the business-oriented devices. So here on the right, you see the expectations for 2020. Without going into the report, what's very important with IoT is that when the costs go down, there will be more scale, because currently it's really a matter of the business case. And the cost is not only the hardware costs, it's a big sum of all kinds of things to be taken into account. So design, development, materials, certification, distribution, commissioning, installation, connectivity, maintenance, support. That's the total cost of ownership. And the idea here is that if those costs, the total cost of ownership go down, then the scale will increase. And you can look at all these individual aspects. We, with the Things Network, focus more on the connectivity part. But we also, knowing this, also take into account design and development, but also maintenance and support, commissioning. That's also part of deploying things on a very large scale. So when LORA was brought to the market around 2014, 2015, this technology is actually one of the first widely available general purpose technologies that is really designed for the Internet of Things. It's not intended to be used by humans, by human interfacing. And well, we have some properties. You can connect tens of thousands of devices for a single gateway. It's very low power. You can send only very small messages. It's like you should compare it to, for example, sensors or devices that can only send tweets, that kind of payload size. And also, if you are close to somebody in general, this is communication, wireless communication, like voice in general. If you're close to someone, you can speak fast and you can speak quiet. You don't need a lot of energy to speak. And if you're further away, and that's with many use cases that are deployed in the field, for example, street lighting, trash cans, things like that, agriculture, you need to slow down the transmission speed, but you also need to talk loud. And loud in wireless communication can mean two things. So this is going to be a bit to the physical layer. You can put a lot of energy on a single frequency, or you spread your communication around a center frequency. And this is the difference between narrowband and a spread waveform. Now, narrowband is very useful in environments where you have control over the spectrum. So where, for example, telecom operators, they license the spectrum, they pay billions for that, and they know which frequencies to use when. But if you're deploying solutions in the unlicensed spectrum, like Wi-Fi and Bluetooth, the 2.4 or 5 gigahertz band, or in the case of LORA, the sub-gigahertz, in Europe around 868 megahertz band, you have to deal with a lot of noise because everyone is using that band. And you can't really use narrowband, because if you use narrowband, then the probability that somebody else is using that exact same frequency is pretty high. So what you do is you have to use a spread waveform, and that's the core of LoRa, where you choose a center frequency and the symbols are modulated around it. And if you put that in time, you see the image there on the right. A little bit about performance, so also a little bit of physics. On the left, you see the TX power of 14 dBm. It doesn't really matter, but it's quite low. You have always some loss in the connector. You can adjust for that by the antenna gain. Then you have the path loss. That's basically the loss that you see during transmission through the air. And then on the receiver side, you have an antenna gain again. It's like an amplifier. There is some loss in the connection, and then that is your RX signal. And the question is really, how low can you go? Because the lower you can go, the further you can reach. So here we have the receiver sensitivity. That's the lowest point that the receiver can actually make sense of very low signal strength. And here we have on the left, basically, you can see what the link budget is. And that's basically the difference between transmission power and the receiver sensitivity. So comparing that with Wi-Fi, TX power is higher. It costs more power. Power consumption of Wi-Fi is quite a lot higher than LoRa. And the receiver sensitivity is also quite high. And it means you get a link budget of 95 dBm. Well, you can do that with unlicensed and licensed. And there's a very nice formula. Unlicensed, by the way, the second row, that's LoRa. In the US, according to US regulations, you have a link budget of 151 dBm. And based on that, you can calculate how far you can go with theoretically. And in this case, it's 850 kilometers. Comparing to Wi-Fi is 550 meters. And it's just based on the link budget, just physics, in perfect conditions. And we tested it together with our community, Things Network community, to see how close can we go to 850 kilometers, to see how does LoRa perform. And so in the community in Utrecht, they created a weather balloon, and they let it up to 26 kilometers. And it was sending messages over Europe. It was somewhere on the border between Netherlands and Germany. And it was picked up by a gateway, TTN gateway in Poland. And that's 702 kilometers. So that's really close to the theoretical distance. And then you would say, why won't you set up one gateway in Europe to cover all of Europe? Well, unfortunately, it doesn't work like that. Because this is free space. And as with all wireless communication, there is attenuation. So that's basically stuff that's between you and the receiver. There's reflection and diffraction, which also distorts the signal. So buildings, signals go not straight, but they can also, just like light, be reflected. And finally, there's the Fresnel zone, which means that it's not only a clear line of sight that you need to have from sender to the receiver, but actually a bandwidth there. So that's a bit of the theory. And all of these different wireless technologies, they have their properties. And it also means that from there you can see what they can be used for best. So this is just a very rough overview of range and bandwidth. And with bandwidth and range, it's also typically from there you can calculate power consumption. So NFC is obviously very useful, very low bandwidth, very low range, but it's even passive. There's not even a battery required in the device. And that's, of course, very useful for contactless payments and tag scanning. BLE, personal networks, so wearables, Wi-Fi, smart home, smart office solutions. And then you have a category of long range, low bandwidth connectivity technologies with LoRa, narrowband IoT, Sigfox. Narrowband IoT is a telecom operator's network, so that's you will always depend on telecom operators to provide coverage. And also it has more overhead than LORA, so it also costs a bit more power. And it will always be subscription-based. LORA, on the other hand, can be set up as private networks as well, because it operates in the unlicensed spectrum, and it means that anyone can set up a network. So farmers can deploy solutions to monitor everything around their farmhouse, up until kilometers of range. But also object tracking, or harbors, or hospitals, where you need indoor coverage, and you need to be sure that there's coverage. And a telecom operator cannot guarantee that you have coverage somewhere indoor in some facility, in some freezer, some industrial freezer. And that's also where LORA is being used, and also where TTN is being used. So this is a bit of technology, back to when we started, July 2015. Fabio is here, actually, he was one of our first community members. It's always good to see him, so there's nothing new for him. Based on this technology, LORA hitting the market, we thought, hey, we can set up a network ourselves, because it's a private network and unlicensed spectrum. The only thing we need to do is buy a gateway and build a network server that implements the server side of the LoRaWAN protocol, and that's it. So we formulated this mission. My partner in crime, Wienke, presented this at the IoT meetup here in Amsterdam. And the next day we started hacking. So this was our first community meeting in the Rockstar building. And I was here working remote. And we had some random people here that were at the IoT meetup, but that were kind of inspired by the idea and were really interested in playing around with this technology. And the initial idea was really to cover the city of Amsterdam with like 12 gateways. And not that we would buy them, that we would invest in them, because they were at the time around 1,000, 1,200 euro, but instead to reach out to companies we used to work for and ask them, hey, do you want to set up a gateway? And they had to pay for it. We would come by, install them, and together we would form one Amsterdam covering network. And well, we needed a prototype to show a use case, to give people some understanding of what we were doing. And so since we are in Amsterdam, we have a lot of canals. We made the most stupid example, but I'll actually come back to this because it's not very stupid. A sensor that you can put in a boat, and it sends a message when your boat runs water. And the reason why LoRa is useful for this is because you can't use Wi-Fi, because you don't know the Wi-Fi access points around the boat. You can't use 3G, 4G. You can, but it's quite expensive. You need a data subscription. You need a pretty good battery. You can't use BLE, because if you use BLE, then you need your phone near, and you might as well look in the boat yourself. And then you run out of options quite soon. And this is a perfect example for LoRa, and also because you don't actually need to send any payload. The fact that this boat sends a message, and the identification is part of the message, so you know which boat it is. You know that's a device that's installed on the boat, and it's a water sensor. You don't have to send the water level, for example. You don't need to send any bytes, in fact. So this was the first use case. Then we gathered. It was basically our second community meeting in Amsterdam. And after that, it really kicked off around the world. Things Network Brazil, for example, they were organizing meetups in TTN t-shirts. Pretty cool. And this is almost 3 years ago. So let's look at where we are today. We are now active in more than 90 countries. There are more than 600 communities worldwide. Just Amsterdam is one of them. There are 3,700 gateways connected to TTN. It makes it the biggest global LoRaWAN network. Almost 40,000 developers, and we are routing 4.5 million messages per day. And that's basically sensor messages that are sent from all over the world, and we route it to the application owner. And we do that for free, and it's an open source stack. We are growing quite fast with the community. So this is also, on the left you see the gateways. None of these are owned by us. So it's really owned and operated by the community. And it's quite dense in Europe. and that's because LoRaWAN is originally from Europe. There are some big commercially operated LoRaWAN networks. So Netherlands, KPN has a network, Proximus has a network in Belgium, Orange and Bouygues Telecom in France, Swisscom in Switzerland. So people know a bit more about LoRa. But we are gaining more and more traction also in US and in Asia, where LoRa also becomes available quite soon. And we are really between the end-device side, so the device hardware side, and the cloud. Normally you would expect just an IP connection. As long as you have an IP address, then you're fine. LoRa devices don't have an IP address. There's no IP stack because that's all way too heavy. That's what the LoRaWAN network server is for, and that's in this case what we do. But in order to make it scale, we have to work on the developer ecosystem. That's one of the biggest challenges. It's not only cost, but also enable developers to build their solution. And if you look at the developer ecosystem today, in the 0 to 1, you can actually build a IoT solution quite fast. You just get a Raspberry Pi, you connect some sensors, connect it to your home Wi-Fi, plug in a USB and an adapter, and you can have a watering plant solution in 24 hours. You use your quad-core Raspberry Pi to monitor the soil moisture, and that's fine. It's cheap, but it doesn't scale, of course. If you want to go to your first batch, so the 1 to 1,000, for example, just as a number, you already have to move towards embedded development. And embedded development today, there are different flavors here, but the two big ones are Arduino and ARM Mbed. For connectivity, you can use LoRa, and you don't have to yet design your own PCB, because there are so many developer kits available in so many forms and so many different flavors that it's typically more expensive to design your own in this phase. And then your solution looks a bit like that, just a LoRa sensor antenna. So how does it work? What does it look like in code? So for example, we have 3 sections. One is on the Arduino, so in this case, Arduino code on the end device. Then we do some decoding in the Things network. And finally, you have your application. And Arduino, like ARM Mbed, most of embedded development today is in C or C++. So this is what you start with, basically. It's very simple. I don't know if you can read it, but it's you define your keys, you initialize the Things network on your end device. You join the network, so that's basically a security procedure. You do that once to join the network. And then in the loop, so that's this section, you read the temperature, and a temperature is a floating point number, and you can't easily send floating point numbers as bytes. So we multiply that by 100, and then put it in a signed 16-bit integer. And so you end up with a buffer of 2 bytes that you actually send over the network. And you basically 25.42, that's the hex value is there. And this is actually, you can compile this, it works, you can connect the temperature sensor, and that's it. In the Things network, you would need to decode this, because this is where you get the bytes in, which are received by one of the community gateways. They are connected to the Things network. We do all the LoRaWAN stuff, and then we execute some very small Lambda functions in the network server that you can program yourself in JavaScript to decode these bytes into an object that makes sense. So this is basically the other way around, from hex to that value. And you need to take care of the sign bit to allow for negative values. But anyway, you end up with the temp 100, which is basically the original value that you also had on your Arduino right here. And you pass that as a JSON object with a key temperature. And then finally, you can build a Node.js app with our TTN package that's on, but we also have Python and Go SDKs. and you connect to your application with your ID, with your access key, and then you can just log the uplink, and you basically receive the value. So that's it. It's very simple to get started. And that basically allows you to build, very simply, to build your first batch, and you can make it all complicated. You can send data back, and you can have triggers and everything. It's super simple. But the problem comes when you really go to scale, when you really go from 1,000 to 1,000,000 or to 1,000,000,000 devices, because then you have to really, you're going to design your own PCB, which makes you really have to look very closely at your bill of materials. You have to select your MCU to use, the battery, also the battery consumption. Maybe with some changes, some if statements, you can save 10, 15, 20% of battery life, which can make the business case already. And so you really need to know very well what your end device is doing, how much memory it uses, and how much computation cycles. Maybe you don't have to develop everything in assembly, but typically you have to know a bit about what's going on there. And the problem is that that is unfortunately the way it is. It's kind of a constant in large-scale IoT. This is not something that is going to be solved in the near future, I'm afraid. The problem is really on this side that the comfort zone of most developers is in Node.js, deploying a Heroku app or doing some Raspberry Pi stuff, which is completely fine. But these are not really worlds that you can combine easily. And so what really needs to be done, I think, is that on the right side, we really need to grow the comfort zone. And fortunately, the industry is working very hard to get there. So major cloud platforms, they have very decent IoT solutions now, IoT platforms. Google Cloud released their IoT platform only a few months ago, but AWS and Microsoft Azure already have IoT platforms way longer. But also we'll see now that there are very small runtimes that allow you to run, for example, JavaScript on the end device using JerryScript, which makes it way more accessible to start developing IoT solutions on the edge. We really see a role for ourselves here between that large-scale embedded device development, because those are typically the devices that are connected to a Things network, and on the other end with the developer zone that we have today, because we only have 20 million developers in the world, which is very, very little. So there are not enough embedded hardware engineers to develop all those 20 billion devices that Gartner says there will be. So let's talk about bananas. This is my grandfather on the left, and he had a family business in bananas. I've never seen this myself, fortunately. The only thing I know, what I also heard from my dad, is that bananas are a very difficult product, because at that time you could only sell them for a week. They were only a week. They were only a week able to sell them, because otherwise they were too green, or after a week they were too brown to sell them. Today that is reduced even, so big supermarkets today, it's like 4 or 5 days, 3, 4, 5 days. But those bananas, they all come all the way from South America, and they are harvested when they are pretty green still. And they look like this, and there's also very accurate measuring today on when they start harvesting them, because the color is the same, but they measure the shape and everything. Then they go on transport in special ships with banana containers, and the banana containers are fitted with all kinds of sensors to control the temperature and the amount of ethylene gas. Because the thing is that you can control the ripening process by changing the temperature slightly. It's a matter of a few tenths of degrees, but also by adding ethylene gas to the bananas. So what you basically want to do is, instead of bringing the bananas in its and keep them as ripe as possible to Europe, for example, or to North America or wherever, you basically want to start controlling, regulating this entire chain also while these bananas are on the ship. And that means that you need to have a downlink connection back to the ship. And that means that you have to connect the whole chain. So let's say, for example, you're in big industry, in your Chiquita, and you want to build a banana ripening app where you want to control the temperature, humidity, and the amount of ethylene gas throughout the chain. You can use a Things network, public and private networks, by using LoRaWAN for the entire connectivity throughout the chain. So throughout the chain means that you can start monitoring the bananas already on the farm, because you can set up a gateway there. You can have a gateway on the ship with a satellite backhaul. You can have a gateway during transport, in storage and in the shop. And actually you use a combination of public and private networks. So obviously on the ship you have a private network, on a farm as well, but trucks, for example, if you drive through the Netherlands, you don't need to have a gateway on your truck because there is TTN coverage, otherwise there's KPN coverage, or both. Also in storage, private networks, and in the shop, private networks, and that allows you to control the entire chain. So that's really, and the reason why this is not currently taking off is because it's very, very difficult to build this. And the market is still working on this, and it takes quite a lot of time. So what is the most popular device today? The mousetrap. And this is actually a real device developed by a Dutch company called Signal, and they built a smart mousetrap. And the beautiful thing about this device, which is super simple, is that you see there a little button, and that physically turns itself mechanically on when it catches a mouse. So basically the device is off. It has almost infinite battery life, and it sends a message to TTN when it's caught a mouse. And that's basically the state of the art today. It's not really true, but it's actually a pretty good solution. We have tens of thousands of these things on our network. TTN stack, and this is basically what we built. So the Things network is a community. It's a community network, but it's also a software stack. And it's we have like a developer portal with forums, Slack, and things like that. And the stack is basically what we spend most of our time on, which is basically building the product. And we are now releasing our version 3, which is better than version 2, because it's more suitable for private networks, and also combining public and private networks. The stack looks like this. So we have different components. Gateways are connected to a gateway server. We have a network server that performs all the LoRaWAN operations. An application server that's basically doing those Lambda functions, but also decryption, a couple of other things. Joint server contains your keys of your end device. Identity server is more like ACLs and stuff. And on the other end, you have integrations. And this is basically where you work with your data. So you can get an MQTT PubSub or HTTP integration, or Google Cloud PubSub, or whatever. And that allows you to interact with your end devices as if they are IP-connected devices, basically. And TTN is a global network, so we operate this from 4 different data centers ourselves. And then we have 2 data centers from community contributions, so in Switzerland and Australia, and they are all interconnected. So a message that's sent from Australia, but the application is in Europe, will actually end up in Europe. And we are working with the community to add this and to create more of these data centers to really decentralize the network. Because we are routing currently 4.5 million messages per day. Well, hopefully that's going to be 20 million next year, and that's actually becoming quite expensive for us. Actually, we have the same organization as Blender. The keynote guy this morning. So we have we have a Things Network Foundation, which is a Dutch nonprofit foundation, and the Things Industries, which is our commercial entity. And we contribute a lot of IP to the foundation, and we also invite other companies to do that as well. And that's also how to make it more sustainable. What's very unique about TTN is that we allow for peering between private and public networks. So this is, for example, the German train station in Berlin. And one of our customers with the Things Industries is Deutsche Bahn. And they are deploying LoRaWAN networks on all their train stations to start building all kinds of use cases. And they start with monitoring, but also controlling the station clocks, which is a very, very simple but good starting use case. A reason not to use a German, like T-Mobile or a German-operated commercial network is because train stations, of course, it's a lot of armored concrete, and it's really hard for them to guarantee coverage indoor. So Deutsche Bahn starts to deploy like 8 gateways on their Berlin train station. And that allows for a lot of coverage, which 8 is almost already too much, but it's more is always better for capacity. And that also gives a lot of coverage to the outside of the train station. And this is very conservative because in reality, because this network is already deployed, we see that there is kilometers of range around the Berlin train station. We have also another customer, it's called My Devices, and they build restaurant-in-a-box solutions. And it's a box, obviously not with a restaurant inside, but with a solution to monitor the freezers and coolers in the restaurant. And for example, if you have a power outage at night, the freezers, they warm up, and all the stuff that was in the freezer defrosts, and then the power comes back, it freezes in again. And the next day when somebody opens the fridge, it's like, oh yeah, it's still frozen, but you basically have to throw it away. And to monitor that, it's very simple. They build a solution in a box with temperature sensors, a few of them, a gateway, and they plug it in the power outlet, put the sensors in the freezers, and that solution works for 5 years. And that's a typical application that runs on top of a TTN private network. And obviously, there are a lot of restaurants around the Berlin train station. So if this really starts taking off, then we'll see a lot of overlapping coverage between these private networks. And our technology allows these private networks to exchange traffic with each other, which is very much inspired by the internet model, because we really see LoRaWAN networks as packet networks and not as the telecom operators. They see it more as a device session network, where everything is based on device sessions. So a device can roam to another network, but then the device is roaming there and not on your home network. And here, it might be that some packets are received by another network, some are received by yourself, but you always want all these packets to arrive in your application. And this is what we provide, and this is private peering, but also this peering works with the public network, the public community network. And the beauty is that if Deutsche Bahn, for example, wants to use the community network as a fallback network, then the rule is that they also have to contribute their coverage back to the community network. So that's TTN. We always say, you are the network. Let's build this thing together. You can build a network by placing gateways. We have a very nice map where you can see where all the gateways are. You can contribute to our code, to our SDKs. Our network server code is on GitHub. You can join communities, which is just very much like meetups. Also people that don't have a lot of technical knowledge, but a lot of knowledge about industries, for example, about sensing or agriculture or healthcare. And finally, on the labs, you can find recipes to share snippets and other solutions with other people. So that's it. I think I have time for some questions.
How much?
Oh, wait.
Ah. How much does it cost to run a gateway, a single gateway?
To run a gateway? Yeah. Well, basically, you only have to buy a gateway once, so it's only a capex investment, because we don't. Nothing is being charged for operating a gateway. So you buy a gateway, and gateways vary in price. The cheapest gateways today are about 120, 150 euro, and very expensive carrier-grade gateways are 5,000, 6,000 euro, and we have both types on our network. And the performance is basically the same. Radio performance differs a little bit. The biggest difference between them is whether they are weatherproof, lightning resistant, and things like that. So you can. We also have our own gateway, the Things gateway, which costs about 300 or 280 euro. You buy it, you plug it in, and you're part of the network. That's basically how simple it is. Yeah.
How secure is it? Because these you have a lot of ranges, of course, the LoRa.
Yeah.
How secure is it for other people trying to tap in to gather data, or is?
Yeah. Did you all get this question? Because my headphones are not working. Yeah, you got it. Okay. So the question is, how secure is it? Security is built in the protocol in LoRaWAN. All messages are encrypted, and there's two levels of encryption. So there is, if you look back here, for example, there's a network server and application server. Typically, and the join server has the root keys. If there's a new session, so if a device joins a network, then the join server, which is basically a trusted server by the owner of the devices. So the owner can also bring their own join server with the keys to really keep control on premises of the keys. And the session keys for a particular session are sent to the network server and to the application server, which can also run in separate domains. The network session keys, which are here, are used for integrity and also encrypting commands on the MAC layer, and the application session key is used to really encrypt and decrypt application payloads. So it's on two layers encryption, and we always advise to control your own join server, which is also an open source product. You can just run a Docker image, open a few ports, and you control your keys physically. And you can also run the application server yourself. So really, you will only be the one to see decrypted data. Yeah, and it's part of LoRaWAN protocol. It's a good question. Yeah.
Another question I had, like in an low density area, like the ships and boats. I get it that you want to maybe do it wirelessly, but for example, at a train station, why is there an advantage to do it via wireless instead of just cabling?
Because it's often very expensive to put a new wired network in an existing building. And in fact, the trend is in building design to do things, in fact, more wireless than less wireless. So we even see new office designs where they allow for infrastructure to place access points, wireless access points within the buildings. But even light switches and lights themselves, they are not cabled anymore for control. But it's a design thing, and often it's more expensive to put cables somewhere than wireless connections. Yeah.
Thank you for your answers.
Hello.
Wait, I'm not hearing.
Okay.
Yeah, sorry.
All good?
Yeah.
How well does the Things network handle increased usage in bandwidth? If I dumped, LoRa. If I dumped 10 million LoRa connected devices in Amsterdam tomorrow, would it fall over? Would you need to have more gateways for these things to access? What's the kind of maximum capacity of one, say, mid-level router?
Yeah, that's a good question. About network capacity, I would be able to that's really enough content for a separate talk. But it's in short, the way we can scale LoRaWAN is by a combination of a few things. We can instruct devices on the MAC layer to use less transmission power, which conserves battery, but it also reaches less gateways. So that means that one message is not received by 5 gateways, instead of 50, for example, by 10 gateways. And that means that the other gateways have more channel utilization left. That's one way. We can increase the data rate, also of end devices. We can instruct end devices to increase their data rate, which has the same effect. Then we can always place more gateways in an area. And what we typically do also with the TTN is to give insight in what the channel utilization is of gateways, and really to see where things are getting full. We are currently working with a data scientist that's are doing research on the traffic, and also to see how our network behaves under excessive load. And we have very good field trials for that as well. We have some areas where TTN is deployed with super dense networks. And that allows us to learn also how it behaves and how it scales best. Yeah. Thank you. Any more questions? Yeah.
Thank you. So, are there use cases where LoRaWAN would not be...
Wait, I'm not hearing you. Wait.
Oh, yeah.
Oh. Yeah.
Yeah. Okay, hi. So are there use cases where LoRaWAN would not be the right wireless communication protocol? For example, I'm wondering about bidirectional communication. Does it allow it? You said it doesn't have IP addresses, so that's why I'm wondering.
Yeah. Well, that also, it really comes back to I skipped that a bit, but there was the idea of this slide. There is LoRaWAN is not a one-size-fits-all solution, not at all. It does allow for bidirectional communication, so you can send messages back. In fact, you can design devices in such a way that they're always listening for traffic. So you can really do street lighting, for example. In street lighting, for example, you don't have a power constraint, because obviously you have to have a lot of power available to turn on the light in the first place. So you can just, the device can listen. And there you use LoRa for its range. You can also use LoRa really for very power constrained circumstances where the device is asleep, almost always, like the mousetrap. Or wake on shake sensors that you can stick behind paintings on the wall in museums, for example, where they only send a message when somebody takes them off. Those are really good use cases for LoRa, but you cannot, the bandwidth is limited. So based on the data rate, you can send between 51 and 220 bytes in a message uplink to the network. And you can only do that, you can only send, due to duty cycle limitations, 1% per band, which is basically in total about 3% of the time. So you have to be silent 97% of the time. And if you need to have more time on air, or if you need to have more bandwidth back to the end devices, then it's good to look at other technologies. But LoRa really fits this area where range is really critical, and where you don't need a lot of bandwidth. And then we see a lot of creative different solutions. Yeah. All right, I think we're out of time. So thanks very much for coming.